like to thank the conveners for inviting me to give a talk, and I hope I don't disappoint them by changing tectonic environments entirely. This is a strike-slip fault talk, well, at least at the beginning. So I'm here to talk about the work I've been doing in my broader impacts, and I have two little stories I'm going to hope to get through. First up, how I conjured an outreach program out of almost nowhere in response to a very late discovered grant opportunity, and that involved high school students in a community in Northern California. And then secondly, my attempts to bring INSAR to a greater awareness amongst geologists and get it taught in schools through trying to develop materials that are disseminated via the web and interactive websites. Okay, so first up, my attempts to do outreach really quickly. My study area, or one of my study areas, is the Bay Area. The Hayward Fault here is considered the most dangerous in the region because it is capable of magnitude 7 earthquakes. It had one 150 years ago. And its recurrence interval seems to be consistent with it being due to have an earthquake soon. But this fault also creeps. So this is PS INSAR data. I'm not really going to elaborate on the full interpretation of it, but you can take profiles through the data across the fault, and what you see is that there's an abrupt jump in the line of sight velocity located at the fault, which indicates that the fault is moving at the surface. And the magnitude of that step gives you the magnitude of the surface creep that is going on the fault. And it's pervasive all along the fault. And at its largest, in other words, the largest step, in the city of Fremont in California. And we'll be visiting there very shortly. So the manifestation of fault creep in a built environment, things break or are sheared over time. Here is a wall with a crack in it that will presumably grow. Here is a winery with the San Andreas Fault running through it. I recommend you go there. It's amazing. It's got a meter offset in the internal walls due to the creep on the San Andreas. This is Berkeley's football stadium before they demolished it and rebuilt it in place. Explain that one to me. And here is a tree on the creeping segment whose roots are going in different directions. And presumably that's quite traumatic for the tree. Creep is important to understand because creep takes away some of the strain that would otherwise be released in earthquakes. These faults are quite rare. That's interesting too. From a sort of fault mechanics standpoint, by understanding it, we might do better at understanding how faults work in general. And the final point is the one I like to hammer on, is that if you understand where a fault is creeping and you can image it well, you can also image where a fault is not creeping, and that's the part of the fault you need to worry about. So I model these INSAR data. I get models like this of the creep rate on the fault, and you can see, this is the Hayward Fault again. Between Oakland and Fremont, there is a zone where the fault creep rate is effectively 0. This is the locked zone on the fault. This is where you need to worry. This is where, more or less, we're in agreement with historical accounts of surface rupture and damage in the 1868 earthquake. So that's where you need to worry. I, back in 2007, was a carefree individual. I just started my faculty position at UCR. I'd been involved in a GPS campaign on the central San Andreas. I was thinner, I had darker hair. Everything was good, but then about 4 weeks after I moved to Riverside, someone sent me an email saying, you should apply for this grant. It's a NASA New Investigator grant. You have to write 20 pages. You have 8 days. And there's a mandatory 4-page education and outreach plan that has to go in here. And we don't just want class descriptions and courses that you're going to teach. We want something tangible, like, oh dear. So I ruminated on this as I was frantically writing. And I came to remember that I had been to Fremont a couple of times as a postdoc at Berkeley. Once when they had a trench exhibit that opened up as a part of the 1906 earthquake centenary commemorations, which was really fascinating. You could go walk down there and see the various offset layers and date potential earthquakes and all that kind of stuff. And when you were there, there was a sign saying, oh, by the way, walk across the parking lot and you'll find evidence for fault creep. Like, oh, really? And then you go to Sailway Drive and there's cracks in the asphalt and the curbs are offset. So I'd been there with my office mate, Isabel Ryder, and we take pictures and goofed off. And I thought, well, okay, if this fault is creeping at the rate I think it's creeping, then those curbs are going to be offset increasingly with time. Can I do something with that? So, note that the time at 12:40 a.m. on the 28th of August, I wrote an email to Jin Liam Kemper at the USGS and said, I think we met. I'm writing this proposal. It's really urgent. I want to do this thing. I haven't got a very good name for it. I'm going to call it Citizen Creep Meters. Get school kids to go out and take pictures of faults. Do you think this has any chance of working? And then I think I stayed up a few more hours and eventually fell asleep, and I woke up quite late the next day, at which point I had 3 emails. One from Jim Kemper. Hi, yeah, I'm swamped with fieldwork right now, but I guess something like this would work if you had some local support. I'm CCing some people who could connect you to Fremont. Joyce Bluford from Math Science Nucleus, a local nonprofit. Seems like a project I could get a team of local high school kids to work on. We've worked with schools in the local area for 25 years. We're also developing an earthquake exhibit. P.S. I am a geologist. This is at 10:04 a.m. So this is like less than 10 hours later. And then the third email was from Patrick McClellan, and it was an amazing compendium of information about educational opportunities and curriculum elements that I could reference in the proposal. Yeah, you should reference the teaching across curriculum, core curriculum, talk about the geography elements, drawing faults, that's important. That means it's across the curriculum, both arts and the humanities. Here are some lesson plans that FEMA has written about faults in areas like this, and here are all the field guides that I know of about the Hayward Fault. So in 10 hours, I basically had a compendium of things. I called Joyce Bluford on the phone. By the afternoon, we'd arranged a budget for her volunteers to have their expenses paid to go out with kids into the field. I had a letter of support, and therefore I had basically a research program, an outreach program in a day. I submitted the grant on the final day before the deadline. Sorry, sponsored projects office, my bad. And it got funded, which was great. So then I had funding, and we went out and we did reconnaissance, and we found all these offset curbs. So this is right by the BART station in Fremont. You can see cracks in the asphalt and a scarp actually through the road. Heavens. This is Rocket Drive, nice offset curb there. This is the Waybell neighborhood where the fault is creeping fastest, and some very ominous looking on-echelon cracks through the asphalt which head towards that house over there, whose garage door does not close. Joyce arranged for high school students to go out and take pictures. This is Joyce, for reference. She's cool. And then the pictures started coming in of curbs, some with feet in, some without, all with a scale, of course, because that's important. We devised a scheme where you had to sort of level and center the tripod above the fault, above the curve offset of choice, and we have several generations of photographs from these. And the amazing thing is that it works. So here is the fault in January 2009. There's your little weedy curve offset. They periodically fix these things, unfortunately. So this one had been fixed relatively recently. 18 months later, another picture. So if I zip backwards and forwards, it actually has moved. And it's moved a centimeter in 18 months, which is approximately 7 millimeters a year of creep, which is approximately what I get from INSAR. So it is amazing. It actually works. If you look at our INSAR data profile fits versus other measurements that Jim Lienkamper and his colleagues had made, our INSAR agreements and their INSAR measurements and their measurements agree, and that particular curve plots right on the trend, right there. Amazing. So I presented this jubilantly at AGU the year after, 2010. NASA was so enamored with the idea of getting school kids to measure fault creep, they actually sent a video crew to interview me. This is me being interviewed and miming my favorite fault movement. They've turned off the comments, unfortunately, but apparently my eyebrows were mesmerizing in this. And that's partly because I think Steve, the cameraman, he was sort of frowning at my face, and I was kind of frowning back at him. But anyway, it's fun. I got 10,000 views, and they weren't all my mother. So what have I learned from this experience? Well, you know more useful people than you think you do, I think is that. Reach out, use your network, and see what you can do. A major part of the credibility of my grant proposal were that I paired with a local organization. They thought that made it much more likely it was going to succeed, and I'd actually budgeted for them to do stuff. They liked that too. And of course, once the idea is out there, people will come and seek you out and try and talk to you about it. So I'm putting myself out there right now. If more people want to talk to me about this, I'm happy to. We've not given up on the idea. This is now 2017, where we're in the brave new world of structure from motion. So now you can take lots and lots and lots of pictures of the curb. We don't need a tripod or to mess around with that stuff. This is work that's being led by my graduate student, Jerlyn, who likes to take selfies with faults. So what we have done is more as a proof of concept at this point. 2-point clouds, one yellow, one blue, as you see colors. And you can see they're actually aligned on this side, so that we made one side of the curb match and looked at the other one. And if you rotate, then actually the 2-point clouds are offset by a few millimeters. So we think this probably will work, and we have all sorts of fanciful ideas which we have not enacted yet about how we could get people with their cell phone cameras to photograph the hell out of these things and then send us the photos, so long as we had someone who was willing to process these images. But we're thinking about it. And if anyone has any bright ideas, please get in contact. Okay, part 2, bringing INSAR to the masses. One of the things I like to do is to make interferograms of earthquakes and model them. Here are some earthquakes that I have at least made interferograms of. Some of them are very cute. This one's in Africa and in Mozambique. This is in the middle of Australia. Who knew? And various other spots. This is work I did with an undergrad at UCR. And in general, we've been compiling these models for a number of years now, with the view to doing stuff with them statistically. Like if you have a sample set of about 150 earthquakes now, maybe there are things you can learn from those, such as why do global seismic methods, teleseismic methods, routinely mislocate earthquakes? So this is comparing our INSAR CMT catalog to the global CMT catalog. You see that there are mislocations. This vector is 10 kilometers long. It's not like we put the earthquake in the middle of the the middle of the Nazca plate or anything like that. No. But there are sometimes systematic errors in these, and sometimes they're pretty random looking. We think it must be something to do with the velocity model that's used to locate these earthquakes, assuming that if you have good INSAR coverage all around an earthquake, you can see where it was, and you don't. Anyway. So one thing we did try with colleagues from the UK, Anna Ferreira at the University College London, and a student we co-advised, Jennifer Weston, was to produce synthetics using much more detailed Earth models made with mantle tomography and the like. And what we found was that, no, they didn't really necessarily help. You can improve the locations of some events, like this Aquile earthquake in Bolivia, much closer to a closer agreement between the locations, but then the Nisqually earthquake goes off scale, and heaven knows what's going here. Basically, right now, even the good Earth models are not that good. That's interesting. That's not really what I'm here to talk about. We can also do things like earthquake scaling. Once you get enough earthquakes and you have measured their lengths and their seismic moments, then you can look for trends in those. And this is something which is useful for hazard assessment. Essentially, if you know the direct dimensions of an unruptured fault, then you can estimate its potential seismic moment. So that's stuff that we can do with these catalogs. But right now, of course, there's so many earthquakes happening, we don't have enough people to model them all. I really hope for the day when I have incoming graduate students who are completely INSAR savvy and I don't have to teach them anything. And that time has not come yet. So in 2012, when I was starting to have these ideas about how great it would be if I could take on already trained or already conversant students, the caption for this on Facebook was "A man, a mountain, and a measuring stick." I was out doing a GPS survey in Whitewater Canyon, and I was having thoughts about, well, okay, most earthquakes that we want to model are pretty simple. Maybe we could do this interactively with some kind of tool. People could do it by hand almost. Okay, and this is kind of what we do when we model simple earthquakes anyway. You get your data, you come up with an elastic dislocation model, and these two look very similar, obviously, and when you difference them, there's nothing left but noise. Well, cool, can we do this? And so we'd hack together some kind of MATLAB code that does something like this, where you could change the vertices of the ends of the fault and change the dip and change the depth of the fault and how much slip and get some kind of forward model. But that's not really what's going to get people involved. So my problem, of course, is that, yes, INSAR is not commonly taught, even amongst the savvy, certainly not amongst the trad geologists. And there's not very many materials available out there to do that. And the tools that do exist are typically very technical and not necessarily for public consumption. So I had this idea in my mind that maybe we could produce some kind of tool that ran on the web where you could just drag and drop the fault around and maybe people could do it, and maybe the public could do it. Who knows? So all these things were kind of rattling around in my head when I went to a teaching workshop in Knoxville in 2012. Jack Lovelace was there also, and a few other of our colleagues. This was to teach geophysics and structural geology. I teach an upper division geophysics class. I wanted some ways to make some of the lab activities a bit more engaging. That was my reason for going. But when I was there, we had a demo from the author of this website called Visible Geology. I don't know if you know it, but it's an amazing piece of technology written by an undergraduate student from Canada, Rowan Cockett. This is he now, looking very corporate and pretending he's not being photographed. In Visible Geology, what you do is you put geological layers into a cube of rock, and then you fold it and fault it and erode the surface. And what you get is the map subcrop pattern, and then you can relate what you see at the surface to the processes that went on down there. And the whole thing is written in Java. It's drag and drop. You can click around. It's incredibly swish. And I went up to him and said, "Have you ever heard of INSAR?" And to demonstrate the problem, he said, "What?" So there you go. But in these workshops, you have breakout sessions where you go and brainstorm teaching activities with other members of the workshop. And I said, "Can you come with me? I have an idea." And I sent him my hacky MATLAB code, and within an hour, he'd coded it up to run in Java and render an interferogram pretty much in real time. Look. Also at the meeting was Beth Pratsatula, who from UNAVCO, who's, I think, going to talk a little bit later. And her eyes were widening as this was happening, because she was very aware that UNAVCO did not have any really good INSAR teaching materials at this time. And here was something that looked the part. And so with some support from UNAVCO, Rowan and I put together this thing. I'm not going to play the video, unfortunately. I think we don't have enough time. But that we'll demonstrate this in the poster hall later if you want to come and play. This tool that runs on the web, you choose your earthquake, you choose your fault, and you draw it, and you change things with sliders and make the patterns match between the interferogram and the earthquake. See, that's why I can't show you. We ran this as a trial activity with my intro class just to see what they thought. They got results that were consistent with the kinds of uncertainties that we would get from bootstrapping our models. They liked it. They wrote nice things, in some more insightful than others. But some indicated they would be happy to do this again. And out of this, and this initial sort of, interaction with Beth and with Donna as well at UNAVCO, I was invited to take part in the production of materials for the geodesy project. And this is a project that tries to use different societal problems as a hook for getting people to use geodesy in their classes. So the sorts of things that I talked about are ice mass loss and surface hazards, and in the module that I was involved with, earthquake hazards. So with Bruce Douglas of the University of Indiana, we went to UNAVCO one cold February weekend, and we're shut in a room for 3 days or 2 days to come up with ideas. And the process went that we'd had a few preparatory webinars where we were taught about the rubrics that they were going to use to assess these materials and the sorts of things we had to consider including in our module that we wrote, all the activities, the learning outcomes, the assessments, the strategies for instruction. I learned quite a lot. We had to get board approval so that we could experiment on our students in our classes, which means asking them questions and asking how they felt about things on surveys. We had to teach it and get these assessments made and then submit them to an assessment consultant to see whether the goals of the module were actually achieved. They were. Right, so the concept was societal impacts, and the tools we were using were INSAR and LiDAR. I don't really have to explain these to this audience, but with LiDAR you can get the locations of faults, you can estimate their long-term behaviors. With INSAR you get a very short-term picture of an earthquake and nothing else. But you get an incredible level of detail of what happened in that earthquake, which could tell you some things about what could have gone wrong. Of course, a lot of people in North America don't live near faults, and so maybe why would they care? But of course, the reason they should care is that there are infrastructure lifelines that will be disrupted by earthquakes that could affect them even if they lived on the East Coast. For example, agriculture in the US is driven by water that crosses, in some cases, up to 5 active faults, or 4 in this case. This is the Hetchy Aquifer Reservoir in the Sierra Nevada, and it supplies water to San Francisco, and that water goes through all these faults here. And then there's another aqueduct that goes to Southern California through this area that carries water for about 23 million people, which I think is the amount of people's water that goes through the Sacramento Delta, which is kind of worrying if an earthquake happened on any of those. So we had 5 units. One was to encourage the students to think about what might happen if such a disaster did happen, and they were very into that, I have to say. Didn't have to encourage them at all. Then we had a module which more or less tries to sort of reverse engineer Olaf Zielke and Ramon Arrowsmith's study of the San Andreas Fault and the different offsets of different ages, showing that there's a repeated cyclical earthquake behavior on this fault. We had an exercise where you see an earthquake from space. In other words, this is INSAR, an INSAR interpretation exercise. We had an INSAR modeling exercise, and then a wrap-up exercise where we provided them with INSAR and LiDAR data for a fault that had an earthquake and some other information, and asked them, well, so what do you think should have happened in this earthquake given what we have told you? And then they went off and wrote essentially an earthquake response report talking about why the things that were disrupted were disrupted. It doesn't stop with producing these things. I'm nearly 2 slides. Once you've made these materials, of course, you're not allowed to get away with just that. Now we are in a zone of publicizing these materials. This is part of my standing here, I guess. Beth has a poster and some of the hands-on demonstrations from geodesy that she's showing in the poster hall. I've given webinars, we've given workshops at conferences trying to publicize these materials, and now you all know about them too. The webinar is at this address, and I'll show you the geodesy address in a minute. So my thoughts so far, really, of course, the one way that these things happen is you put yourself out there. I went to a workshop to learn about teaching, and I ended up coming up with all this other stuff that wouldn't have happened if I'd stayed at home. Identify who might be interested. In this case, UNAVCO was very interested. That was very useful. Of course, if you want to go into the formal route, then you will learn lots about pedagogy, and that will help you in the rest of your job, the rest of your teaching. And on top of this, if you do one thing, other things will arise. So now I'm involved in geodesy. That's great. Thank you very much. Here are my details. If you have any ideas, let me know.